Okay, welcome to the online causal inference seminar. Today we have Eytan Bakshy from Facebook Core Data Science. He will talk about efficient experimentation and inference for large decision spaces. We're very excited to have him here. He will stop from time to time to take questions from the audience, so please submit your questions via Q&A. Then, as a discussant, we have Dean Eckles from MIT. And after the discussion, Eytan Bakshy will again take some questions from the audience if we have time. All right, I'm now switching over to Guillaume, who will handle questions in Q&A.
Thanks, Dominique. So as Dominique said, for questions to Eytan, please submit them via the Q&A. We do not have a co-author, so we'll basically just transmit the questions to Eytan during the breaks if they're selected. So I will ask you to raise your hand if your question is selected. Please don't raise your hand until I've asked you to do it. It makes everything more complicated. All right, that's it on my end. Eytan, whenever you're ready.
Okay, great. Ready to go. Is my screen being shared, or I have to do that now?
Not yet. Yes, now we can see.
Okay, and it's showing the correct set of slides. Perfect. I'm Eytan Bakshy. I'm a research scientist at Facebook, and I'm gonna talk today about some research that my group has been doing over the years. So I'm gonna start off by giving some general empirical context for the work and how we got into doing this work. And then I'm going to talk about the application of Bayesian optimization for field experiments. So Bayesian optimization is a technique that's used for efficient global optimization of things like computer simulations or machine learning models, but we've been adapting it to work for kind of real world internet experiments, and it could be used really for any kind of field experiment. And then I'm going to talk about some extensions to this work, including how we could leverage biased simulations to improve the sample efficiency of these methods. And then I'm going to talk about the use of statistical surrogacy for targeting long-term outcomes through the use of meta-analysis. So I first came to Facebook about 9 years ago, or 10 years ago if you count my internship, to run randomized experiments. Internet companies are a great place to run experiments. It's relatively easy, and a lot of decisions are informed through the use of randomized experiments. But on such a large platform with so many different products and different people, it can actually be hard to figure out, what are the different treatments or interventions or policies that we should be considering. So how should we make inferences in these spaces, and how do we go about optimizing the various objectives that the firm may have? So about 4 years ago, I formed my own research group called the Adaptive Experimentation Team, and our goal has been to radically change the way that we run experiments and develop software, and we do both pure applied work within the company, but we also publish papers and try to contribute to more substantial generalizable knowledge. And so, part of our principles are just randomizing more. We feel that randomized experiments, even though they're very prevalent at Facebook, are still underutilized. And that a lot of experimentation is done without particular goals in mind. This sounds kind of funny, but I think the reality is that when people are running experiments in these real world situations, it's not just a single outcome that one cares about. There's an entire ecosystem that one has to consider. And this can introduce all kinds of issues in terms of modeling and how we want to do our exploration. The other is that we're making the analysis more rigorous, in part through the use of more advanced statistical models or machine learning. And with the aid of causal inference, And these tools were able to identify optimal treatments or policies and more rigorously explore large decision spaces. And so we largely operate in a very integrated model where we might work hand in hand with teams to develop experiments or develop methods, but at the same time, we're building software and we're building these methods. And so this is really kind of a full stack operation where all of the work that we're doing is very empirically motivated. Now, a lot of people think about bandit optimization or Bayesian optimization as a fully automated thing, but there's oftentimes a wide gap between the present practice of experimentation and the notion that we can just automatically get magic. And so there's a whole spectrum of use cases, including ad hoc use by experts, so machine learning, ranking engineers or researchers, to people who are just trained up on these tools, to various self-serve tools, to tools that require no human intervention. So that might be something like, if we're running marketing campaigns, we could run various factorial designs to optimize creatives for promotions using bandit optimization. What I'm going to focus on in particular throughout the talk is Bayesian optimization. And the idea here is that we have very large continuous action spaces, and we wish to optimize multiple objectives within this action space. And so the motivating example for us had been this problem of trying to make Facebook work better in emerging markets. If you think about the over 2 billion active users that Facebook has, people are connecting from really great quality networks to networks that might be 2G or might just have really spotty intermittent internet connection, or really low-end mobile phones from 2011 or 2010. And so it's a real challenge to develop software that works well across all of these different contexts. And so for about 4 years ago, this team of engineers on the Android emerging market team, Alex Cubed, as they were referred to internally, had this idea of saying, okay, well, when people are loading stories, or I guess now when people are loading posts on their mobile phone, should we really be fetching 10 posts every time the user scrolls down to the bottom of the page? And so the idea is that some users might have a really good internet connection, and so we could grab more data, and that way they can have kind of a smoother scrolling experience and they're not having to wait. And we know that the more people wait and the more people are frustrated, the less they use these applications, and kind of all of the metrics that the company cares about goes down. So we might imagine that, okay, if they have a better internet connection, we can load more. If they have poor, let's load less because it takes less time. But you could also imagine other scenarios where if the internet connection is very good, then you can always retrieve more posts really fast. Whereas if you have a poor intermittent connection, maybe we should be more aggressive about getting as much data as we possibly can, because we don't know if we'll be able to retrieve those in the future. And so this is an example of a personalized policy that maps a particular configuration, how many posts to fetch as the user scrolls down the newsfeed, according to what type of internet connection the user is on. And there are a lot of different options here. And you can see that it's virtually impossible to consider all possible combinations. I think there's something like 200,000 possible combinations that are valid if we consider reasonable ranges. And the approach that we're going to be taking is figuring out how to map these policies into vectors, which we can then model through some kind of non-parametric model, such as a Gaussian process. And there are a lot of places where these types of contextual policies or multidimensional treatments come up. So for example, if we had some sort of online game, maybe you could have a mapping of certain skill levels to a handicap. And this might help increase engagement and help people progress through the game at different rates according to their hand-eye coordination or whatever inherent latent abilities. Maybe if you have some kind of mobile app, you might want to have various marketing campaigns or notifications. And you might want to limit these notifications based on their usage patterns. So in some cases, we might have a machine learning model that makes some prediction about the individual. And maybe we want to personalize the threshold at which we actually send the notification based on their usage. So this could be represented as, say, an 8-dimensional policy. You can also think of incentives as a type of multidimensional treatment or policy. Perhaps you have a different consideration for use. And so for those with low consideration, we should offer them more money. We can also view things like menus of donation amounts as one of these vectors as well. Now, one of the most common types of tuning experiments that we use at Facebook are these ranking functions. We call these value models. The idea is that you have some way of scoring content when you're ranking them, let's say newsfeed or Instagram or search results or friend recommendations, where you have a bunch of predictive models of whether a user is going to click on the content. Maybe what is the strength of the relationship between these individuals? What do we know about the producer of the content? Maybe we're trying to stimulate certain aspects of the ecosystem and boost individuals who don't have enough friends or engagement. So these all enter additively into this, what we call value model. And there are these just black box coefficients that we somehow have to tune. And previous to the work that we have and are presenting here, people were tuning this just manually by hand. Now, okay, well, I mean, this still doesn't really solve the problem. They're just a bunch of numbers. So how could we actually model a response surface so that we can make inferences about configurations we haven't yet tried, right? Because we couldn't possibly enumerate the infinite number of possible settings in our value model. What we arrived at was the use of a Gaussian process. The idea behind a Gaussian process is that it's a prior over smooth functions. And so as we manipulate a particular treatment parameter, we might expect the response to change in some smooth way. And so that's something that's like in a very intuitive inductive bias that we might want to leverage. And this first plot here shows 2 draws from a Gaussian process prior. And so this Gaussian process has a long length scale, which means you have kind of a very long correlation between points spatially. So there's a high correlation from one point to the next as we kind of move down the input dimension. This is the output dimension here. If our prior has a short length scale, which specifies, again, the smoothness or the correlation, we get these more wiggly functions. Once we observe data, we can condition on that data and obtain a posterior. And so here are 2 noisy data points. And so this gives an example of what draws from our Gaussian process look like. So possible functions that are compatible with these 2 noisy observations we've observed. So it really constrains the space, at least locally, around the points that we've observed. And depending on this hyperparameter, the length scale, we might see different behaviors of the function. So for example, if the correlation along a short length scale means that you have less correlation as a function of distance, and so you can see that you have more uncertainty between these points, and that your uncertainty really starts to blow up farther away. What we can then do is either infer the most likely values of these hyperparameters, the length scale, and then there's also another hyperparameter, which is how much the function varies in total, the variance. And we can integrate that out through likely values of the length scale. So we could either use map estimation, or we could use full Bayesian inference. And these types of models tend to work really well in practice. When we run experiments that aren't, totally noise, that have a reasonable signal to noise ratio, for most classes of experiments that we've considered, we see really nice performance. So this gives an example of leave one out cross validation, where here is the actual outcome. So these dots represent an arm in the experiment, and these vertical bars are the 95% confidence interval, 2 standard errors the mean. And then the dot, and then its y position is the leave one out prediction and the posterior predicted interval. And so you can see that you not only make pretty nice predictions, but you also get some variance reduction as well, because you're able to borrow strength across nearby points. And something that's pretty desirable from a decision-making perspective is that you get some automatic shrinkage. And so if you have very noisy outcomes, what you'll often see in practice is people get really excited about the result. They'll want to ship it and tell everybody about how great their treatment arm is. But the reality is that you can get all kinds of M-type errors if you do have these really noisy, underpowered experiments. So you get some nice regularization as a result of using these Gaussian processes. So given this model and some objective, how do we go about actually optimizing? Here's an example of a Gaussian process fit to 5 data points, noisy data points, with a mean function and a posterior predictive interval. And this gray line right here represents the unobserved true function. And our goal here is to maximize the objective function. And one of the acquisition functions that's used in Bayesian optimization is called expected improvement. And it's just the area that lies above the best point observed so far. And so, for example, the value of expected improvement over here is just the area above that lies above this point. So it's like the integral of this right here. And so you can see that given this data, the next point we're going to pick is over here. And we can proceed sequentially. And if you're optimizing a machine learning model or a simulation, you would just do this purely sequentially. So you pick a point, you observe the data, the model hyperparameters gets updated. We have new beliefs about where the best point could possibly be, and then we keep iterating. And expected improvement is optimal under the condition that all we want to do is pick the next point and we're going to stop. So it's a myopic acquisition function, and it does a really nice job of maximizing the response surface. There are also batch versions of this that I can describe in more detail at some point in time, but it is possible to select multiple design points simultaneously, and this is what we would typically do in a field experiment. Because when you're running an experiment, things are changing over time, and so you want your experimental treatment to start at the exact same time for all individuals, and it's just as easy to deploy 64 treatment conditions, at least on the internet, as it is to deploy one. So you might as well do multiple at the same time. And so this is an example of expected improvement in practice. So this is an Instagram ranking related experiment. And so this shows the change in a particular outcome for just some random initialization. So oftentimes when we run these experiments, we start with some quasi-random initialization. And this line right here represents the mean of all of these arms. You see that some arms are worse than the status quo. Status quo is this gray line, so this is the 0% change. And when we generate a new round of arms using batch expected improvement, you can see that almost all of the arms are better than the best arm we observed in the previous batch. And so we can proceed in batches to maximize the objective. Okay, so this makes a lot of sense if we just have one outcome that we care about, and maybe we're just interested in improving voter turnout rates or something and have a single objective. But for most firms and probably in a lot of policy situations, we have multiple competing objectives. When somebody runs an experiment at Facebook, they often use a tool that looks something like this. The tool actually looks a little bit nicer than this now, or these days. But the idea is that you can look at many different metrics at once and see how much these metrics are changing. So this shows 0% change, and this shows like a mean estimate and a 95% confidence interval. This experiment is a wonderful experiment because there aren't any statistically significant changes. In general, this kind of thing is a false positive machine, but people do need to consider multiple objectives when running their experiments. And so if we did want to automate experimentation in some way to find what we consider to be an optimal treatment, a lot of things could potentially go wrong if we're not doing what the human does, which is considering a lot of metrics simultaneously. And so, for example, if our goal for the newsfeed experiment was to actually reduce load on our servers or load on the network, what might happen is we might fetch less stories. And that could be good for one outcome, but then it could actually end up tanking another outcome. So here I've put two outcomes. One is the increase in engagement, so how much people are using Facebook, and the other is the decrease in server CPU utilization. So by maximizing this, we're saving money. And each of these dots represents a particular configuration. In this case, these are random configurations that we tried. And by looking at this initial random batch, the first thing you can see is that there are only a few points that are rational, right? There's only a few points on this Pareto frontier where if your preference was any convex combination of these two, you would only choose one of these 4 points. So the first idea that I had was to just ask experimenters directly for some convex combination of these outcomes. It's like, well, why can't you just tell us how much you value this? This is actually a very hard task for decision makers, especially engineers. And so one of the things we settled on was this constrained optimization framework, where the idea is that you say, okay, I want to maximize one particular objective, but I don't want to hurt all of these other objectives, in that we don't want it to deviate from the status quo by more than some amount. And this was really intuitive. And so we made a number of extensions and produced this new acquisition function called noisy EI, which integrates over the uncertainty in the observed data. So while expected improvement assumes that you know what the best function value is, so it's really designed to work for deterministic settings. If you have a really low signal to noise ratio, as you do with a field experiment, a lot of that falls apart. And so we've developed noisy EI to address that, and then it also supports batch computation, which is necessary for field experiments, as well as constraints. So this is available in Bayesian analysis. So constrained optimization is really nice in that it's easy to understand, and it generally maps onto decision makers' mental models of what they want. They usually can very clearly articulate, okay, I don't want to hurt this, but I do want to increase this. But really, they're a hack. People do care about optimizing multiple objectives. People do have multiple objectives in reality. And they're not really flexible enough to account for unexpected trade-offs. So for example, somebody might say, okay, I'm not willing to let this one outcome be reduced by this amount, but then you show them a result and they're like, wow, I can do 8 times better in terms of optimizing this outcome if I just relax this constraint a little bit. And so we've been thinking a little bit about developing alternatives to this. One alternative is preference learning. And so the idea here is that we generate sets of plausible experiments based off of historical Gaussian process model fits. And so we're able to generate kind of realistic trade-offs between outcomes. And then we can use active learning and Bayesian optimization to give individuals pairwise comparisons between 2 different experiments to learn their utility function. And so we can do this using a linear model. It turns out using a Gaussian process as this latent function tends to work really well. And it helps us achieve really nice outcomes. So this is a project that I did with a former and current intern, Jerry Lin and Adam Oving. Another alternative is just full Pareto front optimization. So we just released a paper on arXiv on a generalization of expected improvement where we're improving the hypervolume. And so the idea is that when you run your experiment, you have a particular set of non-dominated points, and you want to push forward the volume of the non-dominated area.
No.
Okay, so we can take a break now for questions.
I think we don't have any questions at the moment. Yeah, sorry, I just broke out of the meeting. I have bad internet at the moment, but no, I don't think we have questions right now.
So, sorry, can I ask a quick question? So if you have especially many arms in your experimental setting, I expect you see some curves of dimensionality that I don't know, after 5, 6, 7, 10, it kind of breaks down. Do you see that, and what is kind of the limit? How much can you handle?
Yeah, so we should distinguish between the number of arms, which is the number of unique design points that you're testing, and the dimensionality of your search space. Mm-hmm. So how many treatment dimensions that you have. With the standard RBF kernel, you do suffer from the curse of dimensionality once you get to something like between, let's say, 18 and 22 treatment dimensions. And the next set of slides is going to be talking about addressing that problem.
Okay, great, thanks. Oh, you have around 15 to 20 minutes left.
Okay.
Thanks.
Great. So these Gaussian processes are really nice in that they're fully non-parametric. You could use them for any type of policy where the policy might affect the state distribution, and the states might affect the outcomes in other states. So they're super flexible, and it works really nicely even on entirely aggregate sufficient statistics. But in some cases, we might want to consider much higher dimensional policies. And in order to do that, we might have to use some other tricks and leverage assumptions based on previous experiments or based on stronger parametric assumptions. So one idea is to use additional domain knowledge for this contextual policy optimization. And this is a paper that I can share with folks if they're interested in. The idea here is that we observe an aggregate outcome, and we have some mixture of states within the population, and we learn what that mixture of states is. And then we assume that across each different context or state, the smoothness of each of the treatment parameters is the same. And that's the model. And so we have a version of that where you just strictly have this additive model, and then we have another one where we leverage an embedding that actually gives us some kind of relationship between the different contexts and how correlated the contexts are. Now, obviously, this adds additional assumptions, but these assumptions might be pretty plausible in practice, and this gives us an example of a policy that's 30-dimensional. This is the leave one out cross validation. If we just fit it to real data, we see we're just predicting the mean and it's garbage. And with this model, we're actually able to make pretty reasonable predictions, including pretty reasonable probabilistic predictions. In practice, it works pretty well. In simulations, it also works well. So we have an example of how to personalize video playback controllers. So we have a simulated test bed for video playback. And this red and blue lines indicate our method versus various other state-of-the-art high-dimensional Bayesian optimization methods that either assume kind of even more structure or assume kind of other types of structure, like low-dimensional embedding spaces. And as a result of this contextual optimization, we're able to achieve not just better results on average, but for every single outcome or every single context, we're able to achieve better outcomes. In this case, the quality of service, quality of experience outcome for each context. So no matter if you're on a poor internet connection or a good internet connection, this contextual Bayes opt ends up giving you better outcomes than the non-contextual policy. So in the sense, it's more fair. I'm going to breeze through this one really quick to get to something that's a little bit more causal inferency. So as I mentioned before, we use these value models for ranking. In some cases, the signal to noise ratio is just too low to really deploy the necessary number of arms. You really need at least something like 3 arms per dimension, at least, to be doing these experiments. So the newsfeed team at some point had developed a simulator so that they wouldn't have to run experiments. It turns out that that simulator was highly biased, and the amount of bias in the simulation really depended on the type of intervention that they were running and the particular outcome of interest. And so it wasn't really possible to just come up with a simple model to debias these simulations. But it turned out if you looked at these plots, there was a clear correlation between the outcomes, which means that we're somehow capturing the structure in some way. And one of the techniques that has been used in the past in the efficient global optimization, Bayesian optimization literature is the idea of multitask Bayesian optimization, where you have 2 related tasks and we can assume some shared structure. So in this case, we're similarly assuming that the length scale, how wiggly the function is with respect to a treatment parameter, is shared across the 2 tasks. And so by using these kernels, what we can do is run many different simulated experiments and then just a few real experiments. And we're able to achieve quite good model performance. For all outcomes we consider, we end up lowering the MSE. We have some tricks for dealing with non-stationarity in the simulator and the experiments. And we have a particular method that we've developed that allows us to alternate between running these real experiments and these simulations to produce successively greater improvements in our outcomes in this constrained optimization framework. So I'll be giving a link to that at the end of the talk. It's published in JMLR. We have some other work that's a little bit more causal, that is related to accelerating experimentation. One of the difficulties with these sequential experiments is that they might just take more time. And because of that, folks may be less likely to use such designs because they're really interested in targeting some kind of longer term outcome. And if we were to just look at the results of an experiment after 1 day or just after 2 or 3 days, 4 days even, these results may not reflect what's going to happen after, let's say, a week or 2 weeks. This might be due to seasonality. It could be due to learning effects or novelties. There might be some actual non-stationarity in the treatment effect itself, not just the outcomes. Or there might be population shifts. So for example, more active users or particular individuals might be more likely to use the service. And so this sample average treatment effect is not representative of the population average treatment effect that we care about. Now, of course, we can adjust all of these things, at least for 1 and 3, but number 2 could be pretty hard. And obviously, people want to run experiments faster. In fact, most people run experiments, at least for newsfeed, at the time that we did this, for a very short period of time. And so what we did is we constructed this corpus of over 100 newsfeed experiments. On average, they lasted for 4 days, and the maximum duration in the data set was 7 days. Now, if we looked at the treatment effect as a function of time on an hourly basis, we would see something like this for an experiment. So this is an experiment with many different arms. And you can see that initially when we first turn it on, we might see a 200% increase in the outcome of interest. But then after about 120 hours, we're in a territory where everything had a negative treatment effect. And so if we're just iterating really fast and we're not waiting the sufficient number of days, bad things can happen. And so how can we go about accelerating this process? The approach that we took is a statistical surrogacy approach. And we did this through a meta-analysis of these prior experiments. And so the idea is that we train a machine learning model that maps between the short-term effects. So let's say the effects of the experiment for a vector of outcomes for the first 1 to 2 days. And then we make a prediction about the outcomes, let's say 7 days later. And then we can use this surrogate model to then make decisions if we wanted to. This is all kind of standard stuff that I don't have time to get into, but there's the original paper by Prentice et al. And some nice work by Susan and Hito and Raj Chetty and others on surrogate indices that has recently come out as well. I think a lot of these assumptions are very plausible in this meta-analysis perspective, especially when we have a large population of these kind of related interventions. In our particular case, we train a gradient boosted regression tree to predict the outcomes after a certain number of days. We end up being able to make pretty accurate predictions, or quite accurate predictions about the 7-day outcomes just using the first 2 days. And we actually have a lower MSE than just using kind of the raw data itself. So it also provides some shrinkage. I'm happy to talk about details later on all of this if folks would like. One of the issues that can come up, which to be honest hasn't been that much of an issue, but we've thought a little bit about it. If we do end up doing earlier termination as a result of using these surrogates, this could bias the results because you start getting a bunch of right censoring because people feel comfortable stopping the experiment short. And so one solution that we came up with is applying a stochastic decision rule where you have some kind of utility function on how bad the outcome is, and that maps to some probability of terminating the experiment. And then you could just use kind of simple prop score weighting with this known propensity score. There are a lot of extensions that one can consider, including treatment effect heterogeneity. If you had access to individual level covariates, one could leverage information about the similarity of the treatments, who's running the experiment. If they're using Bayesian optimization, maybe we could come up with some kind of embedding. And another thing that I think is going to be important is dealing with domain shift, since the types of interventions that people are running over time are changing. The surrogacy conditions may or may not hold as well. So some kind of reweighting could be really helpful there. So finally, I just wanted to give a shameless plug of some of the tools my team has developed. So if you're interested in running these adaptive experimentation, using these adaptive experimentation methods in your own research, we have a package called ACTS. And we also have a package called BowTorch for doing research in Bayesian optimization. And BowTorch achieves state-of-the-art performance relative to other packages. And so ACTS is intended to be used by organizations and software developers, and it can deploy to a variety of settings. And a lot of that is then translated on the back end to BowTorch to actually do the modeling and select the candidates. So I want to thank the anonymous, or so far anonymous audience and the organizers, as well as my co-authors. Here are some references to papers that I discussed in the talk. More publications related to this general area can be found at my website, eytan.github.io. Yeah, and feel free to reach out to me at any point in time. Thanks.
All right, thanks for the great talk, Eytan. I learned a lot. We're now switching over to discussants. So we have Dean will have present some slides, and then Eytan can respond if he wants. And then if we have some more time left, we can take some questions. All right, Dean.
Great. It's a real pleasure to comment on this work. So so I'm going to keep this brief, but there was a lot of interesting material in there. So the first thing I wanted to mention that I think is interesting is just a lot of the literature that you might read about kind of adaptive experimentation, the contextual bandit literature, et cetera, often presumes that we're going to update our design, the probabilities according to which units are assigned to these different arms after each observation. And I think one of the things that Eytan's talk highlighted was how this isn't really how things work in practice. And so a lot of what he discussed was focused on this case of some sort of batch updating, where actually we're running some selection of arms, observing results, and then updating in a batch mode. And so why is that? And I think that's a useful thing to kind of reflect on, as also maybe some of the theory should more accurately match what has to happen in practice. And so one big reason is just that Eytan mentioned is that humans are in the loop, right? That some of this decision making, though we maybe would like to imagine that there's some scalarization of exactly the objective, that's not how it really works. And so humans remain in the decision making process. And the outcomes are not immediately observed, right? So we may have to wait some time to know how some experiment affected the outcomes that we care about. And it's not even necessarily the case that we're getting continuous feedback, right? You would imagine in some settings, okay, maybe we care about patient survival and you only observe patient survival up to some time, right? But actually in practice, say at Facebook, on the timescale that they're working on, a lot of their standard data analysis pipelines may want to wait for a whole day to complete to compute the outcome for an individual user for that day. And so you're not going to update within the day. And another reason you may not want to do that is because there's huge periodic variations in user behavior that have to do with when different people in different parts of the world are online, what they're doing on weekdays versus weekends, etc. So actually trying to update really rapidly may not be desirable actually at all. And so I guess to me that suggests sort of a call for some of the bandit literature to more accurately reflect the big practical benefits to a more batch updating. And that will end up changing the kinds of designs that you'd want to use, because if you are going to send a whole bunch of people to a new design before you observe the outcomes, then maybe less randomization is required than if you were sequentially observing outcomes, because that exploration, you're not going to reap the rewards of that exploration until after, say, a large number of people have been assigned to arms according to that design. So I think that's one of the nice things about thinking about how all of this actually works in practice, even at a very, very sophisticated firm, and sort of at the cutting edge within that firm, is that there's reasons why batching makes sense. Okay. The other thing I wanted to comment on was that a lot of the approach that Eytan described is a little bit different than what you might be familiar with if you're familiar with the contextual bandit or dynamic treatment regime literature. So in those literatures, we often, when we're trying to think about evaluating a policy that allocates people to arms based on their characteristics X or context X, we're going to look at cases where some policy of interest does what actually happened in some observed data, right? So we're going to look at, okay, of all the observations we have from some experiment, we're only going to look at those where what happened in the experiment matches what some policy of interest would do, okay? And so this results in estimators kind of this form, like, so here's a Horvitz-Thompson estimator where we're going to look at observations and weight them according to the probability that the policy of interest, pi, would have actually assigned that unit to the observed treatment, zi, given their context xi. And that this could be a deterministic policy, in which case that, that numerator is either a 1 or a 0. And if it's a 0, that data is not contributing to our evaluation. Okay? So this just plays a key role in all the standard kind of off-policy evaluation estimators in this context. One of the things that's nice about this kind of approach is our statistical inference, say, for comparing two policies. Is one policy better than another policy? Can account for cancellation when two policies agree with each other a lot of the time. So if two policies agree with what to do with somebody who has a particular value of X, then we're always going to know that what happens to those people who have that value of X is not informative about the difference between those two policies. So, so that's kind of a nice thing about actually conditioning on the context and using that explicitly in our analysis, okay? But this is different than what Eytan talked about, which is using Bayesian optimization to try to directly optimize the parameters that define the policy. So some policy pi is going to be defined by, this say rules that map from the context to what action you take for somebody in that context. right? And then we're just going to optimize over the parameters that define that policy, that may define some decision boundaries, or define how many newsfeed stories to automatically fetch depending on somebody's connection type, right? And so my sense is that there could be pretty substantial efficiency losses here compared with actually accounting for what context is realized. But I'm not sure exactly how to characterize those efficiency losses. So I thought that was kind of an interesting point to think about. And also just to note that, again, there might be really good practical reasons why the approach that Eytan is taking to do this Bayesian optimization directly on the parameters, instead of having to keep track of what everybody's context was at every time, et cetera, and the context might be changing within the same unit. I might go from a high quality connection to a low quality connection. And so how does that get represented here? That there's good practical reasons for what they're doing. And so it'd be interesting to think about how can we bound or reduce the efficiency loss from this. And then finally, one of the things that Eytan talked about was using some kind of a biased model to improve precision, right? And so he described this as simulations and as surrogacy. I could think of these as both different cases of some model that might be wrong. So in the simulations he described, really what this is there's some model that involves many parametric or independence assumptions. So the example he had was that we might say that the total actions by some user are just going to be aggregations of the predicted actions for that user for each item in their newsfeed. So how many things is this user going to like in their newsfeed? Well, we're just going to look at some algorithm and say, what would it show them in newsfeed, and what's our predicted probability for them liking each of those things in newsfeed, and then we'll sum up those predicted probabilities, right? And so clearly that model is wrong. It has a whole bunch of independence assumptions, and it could be wrong in a whole bunch of other ways. He also discussed the use of some kind of surrogacy assumptions, where we think some short run effects are going to translate to longer run effects. And this could be a more kind of just sort of reduced form or black box kind of ML model that maps from short run effects to long run effects. But I think in practice, despite actually maybe having some stochastic stopping rule, selection into the samples of sample of experiments that run long enough is determined by the short run effect. So if an experiment looks like it has really negative effects in the short run, people probably are not going to run it for long enough to see what its long run effects would be, right? And different parts of an organization or different people might be more or less patient or more sensitive to periodic or seasonal factors, and so may run their experiments longer or shorter. So we probably want to correct for this in some way using some kind of inverse probability weighted estimator. So one of the questions that this prompted, especially in the case where we have both simulations and surrogate models, and both might be wrong, is there some way to construct multiply robust estimators that combine multiple of these models and are going to perform well even if all but one of them is incorrect? So it seems like there's an opportunity for some recent developments in constructing multiply robust estimators to apply in this setting. So overall, I thought this was very interesting. I was familiar a lot of this work. Eytan and I used to work together on Facebook, but there was also some new pieces. And so I think it's really great to have this view from research-driven practice in this seminar. So thanks for sharing, Eytan.
Fantastic. Thanks, Dean, for the great discussion. Eytan, do you want to respond?
Yeah, I'll just respond briefly so that we can get to the questions. I do think that Bayesian optimization is not appropriate for all cases. My team also works on contextual bandits. One thing that we've observed, though, is implementing things like bandits and especially reinforcement learning is really hard to do well in practice. There's a lot of instrumentation. There's a lot that can go wrong. Logging everything correctly can be really, really hard. And this really sidesteps all of it. Things like off-policy evaluation work reasonably well, but in our experience are still pretty biased. It can be quite biased for bandits, and really not well at all for reinforcement learning. Yet with Bayesian optimization, we are able to do direct policy search for reinforcement learning type problems. So that's I would say that the simplicity and the practicality is what we find to be most compelling about it. But certainly there are advantages of other approaches, and I do think that there's a large space that's a little bit more intermediate, where for now we've really focused on just having these aggregate sufficient statistics. But if you have some decomposition among the states, you can do a little bit better, and you can do kind of more counterfactual policy evaluation and do some amounts of additional simulation from that. And yeah, I totally agree with respect to the doubly robust estimation for the surrogacy stuff. We should catch up about that later.
Okay, cool. So we have a few questions. The people who asked them did not reply to me, so I will just ask their questions for them, and they shall remain anonymous. So first question is, how do you deal with feedback loops when decisions made influence the underlying population, behavior, models, etc.? For example, choosing an optimal policy changes the population or the response of those segments, of some segments. Does the question make sense to you?
Eytan, I think you're still muted.
You're muted.
Yep.
Yeah, it makes some sense. So the contextual model that I described towards the end, where we had that additive decomposition, I would say is like most sensitive to the feedback loops. Bayesian optimization in general is a lot less sensitive to that these feedback loops, provided you could let that policy run for a long time. Now, if a particular treatment generates SUTVA violations, then that's like a whole other can of worms that is really not related to Bayesian optimization in particular. This would be an issue for any kind of experiment or reinforcement learning algorithm that you would have.
Okay. Another question / clarification was about the kind of the surrogate part. So how far ahead are you predicting? Are you trying to predict the effect at 7 days out, or kind of like the long term, like very long term effect?
So for the work that Wilson Tsai and I did with Max Vollendat a few years ago, we were just looking at 7 and 14-day outcomes because that's what we had the most data for. We are certainly interested in outcomes that are much longer timescales. One of the disadvantages of the meta-analysis approach is that the number of experiments that run for 30 days is quite small, and that those classes of experiments tend to be different than the routine class of experiments. They might be kind of holdout experiments that evaluate all changes that have accumulated over the past several months. So using the particular modeling approach that I presented, it would be hard to do something that is much longer than the time horizon that people are actually running experiments. But certainly it's possible but ambitious to do longer term modeling. And that's something that we're actively looking into with more individual level approaches that are kind of a little bit more standard.
Okay. And if I can add just one more questions on this surrogate problem. So knowing that you're going to use a surrogate approach to predict the outcomes 7 days out, would you design the experiment differently, or do you just use the standard experimentation approach and you just tack the surrogate approach on top of that?
Yeah, I don't think we would do. I mean, there are things that one could do potentially and do differently. So, for example, you could imagine kind of learning how to debias your surrogate by continuing to run your first batch and looking at the extent to which your surrogate is miscalibrated. So you launch your next batch, and then you can kind of keep iterating that way. We've also found that multitask Gaussian processes in general can work pretty well for modeling the long-term outcomes. So you can imagine you run your initial subble sequence, your initial batch, you let that run for some reasonable number of days, and then you select some new arms and you keep running that experiment. And then what you do is you use a multitask model to borrow strength across these two, and you make predictions for your original batch. And so you're essentially borrowing strength and kind of learning about relevant parts of the space, but you're also able to kind of adjust and debias using that longer running experiment. So that's something that we definitely want to explore as well. So I think there are ways that you can change the experimentation model as well.
Okay, thanks. That was very helpful. I think that's all we have time for. Yeah.
Yeah, I think we now should slowly wrap up. 1 second. First, let's thank you to our volunteers today. So thank you to Eytan for a fantastic talk and Dean for a great discussion. And next Tuesday, we'll have Malus Mathaus from ETH Zurich talk about total causal effect estimation by combining causal structure learning and covariate adjustment. We're all very much looking forward to that talk, and we hope to see you all there. Again, thanks for coming, and hope to see you all next week. Stay safe. Thanks.
Thanks.